slightly, I mean, we retain the entries that are larger than NP. So let's assume this is like 4, or let's assume this is 3, so I increase it a little bit. I will retain the 4 largest entries. But these 4 largest entries, they are the largest, but they might not be what? The true locations. What's going to happen is that I'm going like, I'm increasing the impulses I'm keeping. I'm taking the 4 largest, but I want to now, within these 4 that are obtained by compressed sensing, I want to figure out which are the true ones. Okay? So now how do we do it? Well, here's what we do. We say this is the impulse noise vector. It's equal to the impulse noise times the Bernoulli vector. Okay? Bernoulli vector, meaning it's a 0 or 1, that is activated with probability P. Okay? That's how we look at the so it's an amplitude times the Bernoulli vector. Okay? And then what do we do? Then we look at we have a hypothesis testing problem. We say either there is 0 impulse, okay, or there is 1 impulse, or there are 2 impulses, or there are 3 or 4, okay? And I'm going to test these hypotheses, okay, and figure out which location it is, okay? So no impulses, S1, these are the sets. S1 contain the largest element of E. So we have the largest, the second largest, the third largest, and the fourth largest, okay? So either no impulse, or the first, or the largest is the location of the impulse, or the first, the largest and the second largest is the location of the impulses, and so on, okay? Okay, then what do? I'm going to find the probability of the location, maximize the probability of the support given Y. What does the support mean? Support means the location of the non-zero, okay? So how do I find this probability? Well, okay, so I want to find argmax over all S's given Y. So by Bayes' rule, it's going to be probability of Y given S times P of S divided by P of Y. P of Y is irrelevant because it's the same for everybody, so I want to maximize this. I want to find the map estimate of the support. What's P of S? What's P of S? P of S is the probability of the Bernoulli vector happening, right? So if I have 1 entry, that probability would be P times 1 minus P to the power n minus 1. If I have 2, it's going to be P squared times 1 minus P to the power n minus 2, and so on, right? And this is Y given S. Okay, so Y given this support. The minute I have the support, and the support is Gaussian, it's easy to find what this Y is, right? Because Y is equal to A, E plus noise. A is known, E, I have figured out the support, plus noise, A times E is Gaussian, the noise is Gaussian. I'm done, right? So I can't find this. Okay, so this is what I was saying. P of S is given by this. And this one here, because Y is Gaussian, given the support, I can find this distribution, right? All I need to find this distribution is to find its covariance. This is the covariance, okay? So this is probability of Y given S, okay? And then that's it. So I maximize this. What's going to happen is this. I have basically 2 factors. This factor increases with S, right? This factor here, sorry, decreases with S. And this factor increases with S. So there is tension between the 2 factors. Okay? So I'm gonna reach a maximum and then come back. Okay? And that's how I find the location of the true support. Okay, once I have the location, so remember, the sparse recovery problem is 2 things. It's a 2 problem. Basically, I find the location of the support first, and then I find the amplitude. Once I have the support, the amplitude is easy, right? It's a least squares problem. So I found the support, then I solve for E. It's going to be A sub S meaning I'm taking the matrix and I'm retaining only the columns corresponding to the location of the non-zeros. So I can do a least squares or a linear MMSC solution. Okay? Okay. Okay, so if I do this, let's see the gain we get by doing this. Again, this is the perfect line. This is the line where I retransmit. This is the line where I consider things to be Gaussian noise. Okay? And this is the line of compressed sensing, just using L1 to estimate the noise and cancel it. Okay? What's the next line? The next line when I do L1 and then follow it by refinement. Okay? Okay? So that's what we gain. So one question that basically to end this part is, what if what we assumed here is the sparse vector is Bernoulli Gaussian. But what if it's not Bernoulli Gaussian? Okay? What if the amplitudes are not coming from a Gaussian distribution? What happens in this case? Okay? Okay, so what we've done so far, just to summarize, we've seen that if we want to solve this system of equation, when x is sparse, undeterminate of equation, solve the L1 problem, and then refine it statistically. Okay, that's what you could do. But there are several problems with this approach. First of all, although we can solve it in polynomial time, okay, it's still complex. That's one. The second problem is that we cannot use a priori statistical information. We use the a priori statistical information, if you want, in a clever way. But can we use the sparsity information and the statistical information together? Okay, that's which we don't do. And finally, what if we have other structures? What we have here, the only structure we use, what's the only structure we use so far? The only structure is the fact that x is sparse. But I might have other structures in A, X, or Y that I could use. Okay? So, so we're gonna tackle this in the following. And yes, please.
I have a small curiosity question. Instead of this this hypothesis testing.
Yes, yeah.
Maybe I would have taken something like MDL to find the good number.
You mean the good number? The good number of what? You mean
the size of this, the cardinality of this.
Yeah. Okay.
How does that compare?
We haven't tried it. Actually, what we do is we use de Moivre's theorem to get even a better. So we find the probability that S is the probability probability of S is greater than R is less than or equal to 0.01, for example, using de Moivre. But I mean, it would be interesting to Exactly, yes. But this is what you're asking about, right? Yeah. But that's an interesting, yeah. Okay, so as I said, what the talk is organized around structures and applications. So the first structure is statistical structure, and this is work done by Mudassir Masoud, who's a PhD student at KAUST. Okay, so we want to solve this problem. This is what we want to solve. Now, ideally, I would want to solve it using the optimum MSE. I want to find the expected value of x given y, okay? But this is very difficult. Now, if I know the locations, if we know the locations of the non-zeros, things are easy, right? We can all go home if the locations are known, right? This would be least squares or linear MMSE. The problem is that I don't know the location. So since I don't know the location, the way to solve it is this. Expected value of x given y, this is the optimum estimator, right? The optimum MMSE estimator is equal to the following. It's expected value of x given y and the support multiplied by the probability that this support happens. Okay? So it's multiplied by p, probability of s given y. Okay? Now, what's this? Well, again, by Bayes' rule, this is P of y given S times P of S divided by P of y. Okay, so how do we find these? Well, as I said, what we do is we model the vector as a product of two vectors, a vector of amplitudes and a vector of Bernoulli variables, okay, as we done here. Now, what people did in literature, they have always assumed that the amplitudes are Gaussian. But in many cases, they are not. You cannot assume them to be Gaussian. And the question is, how do we go about this problem? Okay, so what we assume, the statistical structure we assume, if we want to be generous with ourselves, we can say that the noise is Gaussian. That's fine. But X, we cannot assume it to be Gaussian. We can assume it to be Bernoulli something, where this something we don't know. Okay, so what we're going to do, we're going to show you an approach where we can solve this problem. So basically, it's going to be agnostic to the distribution of the amplitudes. Okay, and it's going to only kind of acknowledge the Gaussian statistics of the noise. So how do we do it? Okay. So we want to find this, which is basically the optimum MMSC. And to find it, we need to evaluate three terms: the expectation, this probability, and this summation, okay? And we want to do it assuming that the amplitudes are not necessarily Gaussian, okay? This is the important part. Okay, let's go evaluating these one by one. So the expectation. How do you evaluate the expectation? Well, I don't have, the signal X is unknown for me, okay? The distribution. So what do? My best bet is to do a blue. So if I know the support, okay, my best bet is to find the blue estimate or the least squares estimates, okay? So this is for the expectation, this part here. I know the support here, I'm conditioning on the support. Okay, now let's find the probability of S given Y. This is given here, okay? PS, we said it's Bernoulli, so this is easy to calculate, right? This is easy to calculate. Now, what's difficult is to calculate P of Y given S. P of Y given S, in the previous case, we said if it was Gaussian, life is easy, right? But here we're saying X is not Gaussian. The unknown is not Gaussian at the support. So how do we do it? This is how we do it. We know the support, right? We're conditioning on the support. So given the support, Y is equal to A sub S, X sub S plus noise. What we're gonna do, we're going to project this Y here on the orthogonal complement of AS. Okay? So this is AS here, this is AS, Y is a vector here, it's a vector here. I'm gonna project Y on the orthogonal complement of the space spanned by AS. Okay? Meaning I'm gonna multiply Y by this matrix. What happens if I do this? And I'm going to only retain the component that doesn't include any contribution from this. Is that clear? And so I'm going to kill the noise component. The signal component. Okay? So if I kill the signal component, what am I left with? The noise or the projected noise, right? So we can say that approximately, so we're going to have P of S perpendicular times Y. This PPS perpendicular times Y will kill this part and will give me only this part here. This is Gaussian. So I can say approximately my PY given S is given by this Gaussian distribution. Okay? So this is how I find P of S given Y. Okay, so we found this is least squares. This is by projection we found it. It remains to find this summation. The sum is done over what? The summation is done over what? Over support. How many supports there are? It's 2 to the power m possibilities, which are large summation, right? So I want to now evaluate this sum in a greedy manner, okay, to reduce the complexity. Okay, so this is how we do it. We find the best first support, the best place where I think there is non-zero, and then I add supports to it, okay, in a greedy way. Okay, so this is the best element here, meaning the element where there is the largest value of non-zero, and then I find the next one, and so on. Okay, and the good thing here, this is like an order recursive problem. You can, when you want to evaluate these values here, you can do them in an order recursive way. So that would do what? That would reduce the complexity. Okay. Okay, so just to summarize, if you're lost, this is done. I'm saying the summation over S, where S is the support. If I know the support, this is easy. This is least squares. This is done by projection, and this is evaluated using in a greedy manner. Okay, and that basically gives us what's called the SAB-MP, support agnostic matching pursuit. Okay, it is agnostic to the support or the distribution of the support, and that's why it's called support agnostic matching pursuit. And it's a very interesting algorithm for a simple reason. Okay, we have two types of solutions. Solution one, which is based on L1. Remember the L1? The problem with the L1 is that it does not use any statistics. It does not use any prior statistics about our problem. On the other hand, we have the Bayesian approaches, which assumes what? Assumes that the noise is Gaussian and the sparse vector is Gaussian, right? We are in the middle. We assume that the noise is Gaussian, but we say nothing about the distribution of the vector x, okay? This is one thing. The other thing also, it's a greedy algorithm, and because it's greedy, it's fast, Okay, so basically it's kind of like, you know, getting the best. So these are the various approaches, the L1, the Bayesian, the greedy. We are getting the best of all worlds, okay, in this algorithm. And this can be seen in the simulations. Okay, so first of all, another thing which is important here is that the parameters I need to estimate are very simple. Just the variance of the noise and the Bernoulli probability, okay? Which is basically reflects how sparse the vector is. That's it. I don't need to estimate anything else. And that's why, and we can estimate them as part of the algorithm. So let's see some simulations. Here I'm simulating the mean square error I make versus how sparse the vector is. So this is the sparsest, this is the densest, okay, the rest is sparse. The red line is our line, okay? This one, for example, is using L1, okay? Which, this is L1, which is very bad because it doesn't use statistics, right? It's very bad. This one here, assuming that, this is basically the Bayesian that assumes that the signal is Gaussian. Now here in this simulation, what type of signal I'm using? My X is Gaussian. Even in this case, we are able to beat this algorithm. Now if we use a non-Gaussian signal, okay, we can repeat the process for non-Gaussian sparse vector. This is our algorithm, this is the L1. These are the Bayesian algorithms, and as you can see, we also beat them. It makes sense to beat them here. Maybe someone will say, how come you beat them here? Okay, very good, okay. So why do we beat them? Because actually they are using a greedy algorithm as well. If you solve the exact, we're not solving the exact problem, remember. The exact problem means I have to sum over the whole S, right? But it turns out, it seems, that's what it seems, is that our approach is robust. If you make a mistake in the greedy approach, we're robust to it, if you understand what I'm saying. But if you solve the exact problem in a Bayesian way, then, well, maybe they'll beat us. Maybe they will beat us, if you understand what I'm saying.
It's not with the greedy, with the complete one.
Yeah, with the complete, they will be, I'm not sure if they will be the same or better. Okay? Okay, now some will say, okay, you know what, you're gaining in performance, probably you are more complex, right? Well, let's see the complexity. This is the complexity, the average runtime versus the sparsity. And as you can see, our algorithm is also the fastest, okay? The other algorithms are much slower. Let me see. Okay, I don't want to, okay, this is another interesting figure. Here what we're doing is this. We take the vector here and we generate it, we take the same sparse vector and we make the amplitudes once uniform, once Gaussian, and once Laplacian. Okay? And we want to see the difference in performance in the mean square error we make. Notice that the mean square error we make is independent of the distribution. We make the same mean square error regardless of the distribution of the non-zero entry, which kind of like, you know, says that we're truly agnostic to the distribution. Okay, now here we've done this, someone will say, okay, you know what, your algorithm works well because your signal is really perfectly sparse. But what if the signal is not really perfectly sparse, right? It has a few large elements and lots of small ones, okay? So in this image processing example, okay, we're trying to estimate this image here, using its wavelet transform. And we can see here, this is the performance of our, this is the error we make, and this is the error that other algorithms make. And you can see our error is darker, meaning our error is less. Okay, so just to kind of conclude this part, what we've done is the following. We've solved the underdetermined system of equation for a sparse vector in 3 ways. Okay, the first way is L1. The second way is the map solution. You find the optimum support and then you estimate it, or the optimum MMSC. The optimum MMSC, you can do it in 2 ways, the optimum MMSC. Assuming that the signal is Gaussian, right? The unknown is Gaussian, or assume that it is what? non-Gaussian, or I don't know the distribution. Okay, so, any question before I move on? I don't know when we're breaking or where. Yeah, yes.
The compression rate, so you give this logarithm of something that depends on S, but you don't know S.
Yeah, so basically, I mean, that's always the case. You don't know S. So, I mean, you have to be generous a little bit. I mean, you don't really like, be too conservative,
It's just how to choose practically the compression rate, yeah.
Well, here's the thing. I mean, if you don't, you need to know from practice what S you expect. But here's the thing. Even if you reduce the number of, let's assume that S is 2, and you use, instead of 2 log n, you use log n. What's going to happen, you're going to have a graceful increase in error, if you understand what I'm saying. Yeah. So the more equations you put, you're going to reduce the estimation error. You can look at it in this way. Okay. It's not like, you're going to perform very badly and suddenly you're going to succeed, right? Things are going to change in a graceful way.
But then I will return to the question from Luc. If you estimate the dimension blindly of your signal, you can use this as the S, maybe, or.
Right. Yeah.
Could be.
Yeah. It could be, definitely. Yes.
Thank you.
Okay. Any questions? Okay. So what I said, remember, what we said is the talk is organized around structures and applications. Okay, the good news is that we have more applications. We're just now doing theory. We just did one application. But I want to go for one more structure before I have more applications. Okay, so the first structure is the fact that the noise is Gaussian. We use that, right? Now, what if the matrix A is structured? Now, in many problems in signal processing and communication, A is not random, and most of, for those who work in compressed sensing, they know that most of the theory assume that A, the sensing matrix, is random. But what if it's not? In our problems, A is toiplets, it's an FFT matrix, it's something like this. In particular, in the impulse noise example, if you remember, we used the last carriers in here. So we used a truncated FFT matrix, okay? And that is very highly structured. A truncated FFT matrix, if you want, is a Vandermonde matrix, okay? And the question is, can we utilize this? Can we utilize this structure? Okay? So there are lots of other structures here that I list here with some references. Okay? So let's see. Let's assume that A is, for example, toiplets. If it's toiplets with a finite support, what's going to happen? As you move on, the columns will become what? So you have a few non-zeros, it's toiplets, and then you move on, right? So if you compare this column with this column, what can you say about them? They're orthogonal, right? It's a translation, that's a translation, but they are orthogonal as well, right? Okay, now the same, so here's what I'm doing. I'm taking a toiplet matrix and I'm correlating the center column with the remaining column. And you can see that, you see the correlation is high and then suddenly it becomes 0, right? Now the same thing can be said about the truncated FFT matrix. If you take an FFT matrix, a full FFT matrix, any two columns are what? Are orthogonal. If you truncate it, what happens? The columns are no more orthogonal, but what happens is that as you move on, they become less and less correlated. So you can see it here. This is the correlation of the center column with the remaining columns, and you can see the correlation is dying out. Okay? Now why is this important? Let's see why this is important. Let's assume your sensing matrix is orthogonal, okay? And I want to solve y equal to ax. Solving it would be easy, right? Right? Solving it would be easy. Because if you do the least squares problem, it's an A Hermitian A times A Hermitian Y, right? But A Hermitian A is what? If they are orthogonal. It's going to be identity, right? So basically, to find the x, I need just to correlate A with y, right? In fact, if you have, let's look at it this way. I have this y, and I want to find its components with x1, x2, x3. What do? I correlate y with this vector. I independently correlate y with this vector and with this vector, and I get the The components, right? So this is if what? If the columns are orthogonal. But in our case, the columns cannot be completely orthogonal. They can only be semi-orthogonal. Why is that? Why can't they be completely orthogonal? It's a fat matrix, thank you. It's a fat matrix. So there are more columns than rows. So I cannot really have them completely orthogonal. But in these applications that I mentioned, the toplets and the truncated FFT, this is what happens. What happens is this. I can group the vectors into semi-orthogonal columns. So what's happening here, if you want, these are vectors here, okay, which are highly correlated. And these are vectors here, which are highly correlated, and so on for these vectors. But when you look at this set of vectors and this set of vectors, they are what? They're almost orthogonal, okay? And that allows us to solve the problem in a divide and conquer manner. So what we do here, this is what we're solving. This is y equal to a x plus noise, okay? I can subdivide this matrix into chunks, which are what? Essentially orthogonal, and solve each one of them separately, okay? So this is what we do. And so the original problem, remember the original problem was this. Find this optimum expectation. Now, since they are orthogonal, I can subdivide the x into small pieces, and I find the expected value of x given y independently from the remaining x's, okay? And why is this good? Because now this summation, you know, the biggest problem is this summation, right? And we did it in a greedy way. Now this summation can now be made much faster, okay? Because now what I'm going to do, basically, when I solve the problem, I'm going to look at s's that belong here, and s's that belong here, and s's that gonna belong here, okay? So that's why, okay? So so this is one way. So basically, in other words, we solve the problem in a divide and conquer manner, and that comes from the structure of the sensing matrix. But there is various, now, okay, I know many professors here work on adaptive filters, and this is my background. My background is adaptive filters. So the big question is, can we reduce the complexity even further? Okay, and this is how we can reduce the complexity. So there are basically three sources of complexity reduction that we can make use of. The first source we've already talked about, which is the fact that I can group columns into orthogonal or semi-orthogonal vectors. The second one is that the clusters are similar. And the third one is basically recursive implementation of the algorithm. So let's see what I mean by that. First, we talked about the orthogonality of clusters and how it allows us to do things in a divide and conquer manner. Now let's talk about the similarity of clusters. So here's imagine this is an FFT matrix or a toplets matrix, okay? And I'm looking at two clusters. This is cluster 1 and this is cluster 2. These are far enough, so they are going to be orthogonal, okay? Now here's what's interesting. This is one of the cones, and this is another cone on two different axes, okay? The relative positions of these columns, these are like, you know, I have so many columns here within the cluster corresponding to this cluster. So here I have 3, The relative positions of these 3 points is the same for this one and this one. Their relative position is the same. And because their relative position is the same, many calculations are the same. What do I mean by that? For example, if you take this matrix, A1 Hermitian A, and you compare it with AI Hermitian AI, the value is the same. Okay, why? Because the relative positions of the columns are the same. To make it more precise, this is A1 and this is AI. What AI is composed of the same columns of A1 modulated by a single vector here, A delta I. So this vector here, this vector is the same for all columns, okay? And it's a function of the distance. So what it means is that AI is very similar to A1. So when I multiply AI Hermitian by AI, by itself, okay? I will get basically the contribution of these modulating vectors will what? Will go away. Okay, these are like complex exponentials, right? You're multiplying complex exponential by its conjugate, what's going to happen? It's going to disappear. Okay? So that, yeah.
That's the case for a FFT.
FFT, exactly. But
Not for the tuplets.
very good, not for the tuplets. However, the tuplets, what's going to happen is that these shifted versions of each other, one shift, and this is also one shift, right? So it's the same. Okay? Okay, so for example, when I want to calculate, remember, I want to evaluate this thing here, right, with the probability and expectation. So I need to evaluate, for example, things like this value and this value. So the determinant here will be the same for both this cluster and this cluster. Okay? So in other words, I need to make calculations for one cluster and then pass them on to the other clusters. Okay, so for example here, I want to calculate, for example, something for cluster I. For cluster I need to calculate this weighted vector, y weighted with sigma I. It turns out that this value is the same as this value, which is what? Which is y weighted with this matrix computed from cluster 1. The only need that I need to change is that I need to modulate y with a certain vector. So in other words, this matrix need not be calculated again. I already calculated it here, and I just need to modulate this vector. Similarly, the determinant here of this matrix belonging to cluster I is the same as the determinant of the same matrix, okay, containing the same group of columns, okay, for cluster 1, and things go on. Okay, so in other words, do things for cluster 1, do the things for one axis, and then transport the values for the other axis. Okay, so this is, and then we have various recursions here. That happens because of this. Okay, finally, I can do recursive evaluation of things. So basically, like, I want to calculate things for one column, and then I want to add one more column in this cluster, and one more column in this cluster. And then I want to add a third column in this cluster, and then a third column in this cluster. How do I do it? Well, I've calculated things for the first column. I add one more. I can do the calculations recursively. And I add one more. I do the calculations recursively. When I'm doing this recursive calculations, I can transport all the calculations I did to the other cluster. Okay? So this is basically how we can make heavy use of the fact that the matrix is structured. So, and this results in drastic performance improvement. So let's go back to our impulsive noise example. In the impulse noise example, we said that this is the probability of impulse, and this is the rate. This is the performance when I know the locations of the impulses exactly, okay? And, okay, this is the performance of compressed sensing, L1, refined compressed sensing. I do compressed sensing, and then I do statistical refinement, okay? This is the exact algorithm where I don't use structure, and this is the algorithm with structure. And as you can see, they are almost the same. Okay? So what did we gain? The performance is worse, right? What do we gain? We gain in complexity. Let's look at complexity. This is the gain in complexity. We are orders of magnitude faster because we are using the structure. Okay, so what we've done so far is we've used the statistical structure, okay, the fact that the noise is Gaussian, and we use the fact that A is structured. So these are, so we have four variables, y equal to A, x plus noise. We've used two structures, the structure in A and structure in noise. So it remains what? It remains structure in X and structure in Y. Okay, okay, any questions? Okay, so let me go through the another piece of structure, which is structure in X, and basically block sparsity. Remember, when we have a sparse vector, we said we have two things we need to estimate, right? The location and the value at that location. Now, in many applications, the location becomes is a block location. And because it's a block location, it's easier to find. If you go back to the tire puncture, okay, So like, if the puncture is very small, it will be very difficult to find, right? But if the puncture is wide, it will be easier to see, okay? So what we did is, remember the SAB-MP algorithm, the algorithm which is basically agnostic to the distribution of the distribution of the vector, of the sparse vector. We extended it to the block sparse case. So in the block sparse case, we have, so what happens is that the unknowns come in blocks. And because they come in blocks, they're easier to locate. So we extended our algorithm to the block sparse case. And this is how we perform. This is the performance of our algorithm this is the number of active blocks, and this is the error. This is how we're doing versus other algorithms. And this is the performance, and also we beat them. This is the success rate, meaning how successful are we in recovering the sparse vector, and this is the success rate. As you can see, our success is higher than other algorithm. Okay? So this is basically the structure in the vector X. Okay, so any questions before we move on? Yeah, please.
So what is the relation between the width of each block in block sparsity and the width of the clusters when we consider the structure of the matrix A?
Okay. So what you're saying, are you talking about block sparsity?
Yes.
Okay, we don't. We did not investigate this. We did not investigate, but you see what happens is this. When you have structured A, what you do is you try to find the. We did not do the link between the size of the block and the cluster size. But what we do is this: whenever we do a cluster, we do an initial investigation of where the non-zeros are.
Within the cluster.
For the vector, okay? For the vector. How do we determine the clusters? We do an initial investigation, and then we draw a circle around each. Possibility of where the non-zeros are, and we make sure that the circles are not overlapping. If they overlap, then we make them into a single cluster. I don't know if this is clear. Okay? Okay, so, okay, maybe how much time do we have before we break? What time is it? So what time is it right now? Sorry? 15 minutes are left. Okay. So let me give this application. Yes.
You were talking about overlapping.
Yeah.
Wouldn't it be helpful if the clusters were overlapping with each other?
No. If they're overlapping.
Yes.
Here's the thing. Remember, we said we have cones, right?
Yes.
And these cones, the columns of the cones are they should be kind of orthogonal, right?
Yes.
Now, if the clusters are overlapping, what needs to happen is I need to put them into
the same circle.
The same. So in another way, if you want to look at it, if you want to use the cone example, the cone becomes wider.
Yes.
Because it's going to include more.
Okay.
You see what I'm saying? It becomes wider because I'm going to increase the cluster size. Because if I treat them to be independent, the columns might not be orthogonal. Do you see what I'm saying?
Yes, but I thought it would be helpful if they, if I can, talking about decoding, if I can decode one cluster, it will be helpful to help to decode the other one, even though they are not orthogonal.
Right, but I mean, the algorithm doesn't work this way. The algorithm, for it to work...
I'm suggesting some idea.
Yeah, no, I agree with you. I mean, you could do it in an iterative way, but the algorithm doesn't, you could do it in an iterative way. Like, find one cluster, and then find the next, and then find, again, the first cluster.
Yes.
But then you cannot do all these fancy things I showed you.
And it won't be helpful in terms of complexity of decoding.
Exactly. It will be worse in terms, yeah.
I don't...
Yeah.
Thought it, as much as the clusters are overlapping with each other, it would be helpful to reduce the complexity in decoding. I will be gaining in terms of complexity. No, I don't know. I'm just...
No, because, okay, maybe you have to do another algorithm. But
yes,
using my algorithm...
yes,
yeah,
okay.
Yeah. Because my algorithm is based on, like, transport...
Orthogonality and...
Yeah. So this will not happen anymore. So...
Okay, thanks.
Okay, so this application, so all my applications I'm going to show are come from signal processing. This is one of the, basically perhaps this is the only application that is pure communication or even has, like, an information theory perspective. So basically it's feedback reduction in MIMO broadcast channels. Okay, so in broadcast channels, what we try to do, so we have 3 antennas, and we try to serve a number of users here, right? Now, what we want to do, basically in opportunistic communication, we try to, like, look for the strongest users and serve them, right? That's how we do opportunistic communication. And then how do we, so these are the strongest users here, we try to serve them, but because of the motion of the users, we know that whoever is strong now, later on will be what? Will be weak, okay? Now in particular, we apply a technique called random beam forming. Okay, so we basically form beams using these 3 antennas, and we try to ask the users, what is the strength of each beam for you? Okay, so here basically we have 3 antennas. The antennas are going to create 3 beams, and each user is supposed to find the strength that he has, the SINR of each beam, and feedback decide which beam is the best for him, right? And feedback that strength to the base station. Now, what's the problem with this approach? The problem is that if you have many users, the base station has to wait for all the users to feedback before it decides on which one to serve, right? But that time, like, the users have moved, right? Or like the feedback time will be very high. So how do we decrease it? Okay, so how do we decrease it? Now, what the problem with this? The problem is that I have to dedicate a special time or special bandwidth for each user to feedback his channel, right? Now, how do we solve this problem? The one way we solve it is we say, okay, only if your channel is strong enough, is above a certain threshold, then feedback. Otherwise, remain silent. But this doesn't solve the problem. Why? Because I still need to dedicate time for each user, because I don't know which ones are going to be strong, right? One way of solving this is what? Is to do what? Like Aloha, right? Aloha type of algorithm. Like basically users send, right? They contend, and if there is a collision, they back off, right? That's how we usually solve it. But you can solve this problem also in a compressed sensing manner. So the way we do it is the following. This is the sparse vector of you. This is what the users want to feedback. They're going to feedback the strength of their channel, right? Now, many of the users are going to be silent. Why are they going to be silent? Because they are below a certain threshold that the base station will determine. So this vector is going to be sparse, okay? Now, what we're going to do, we're going to assign a code for each of these users. So user 1 has this code, user 2 has this code, etc. Okay, and so what the base station is going to receive the multiplication of this matrix by this vector plus noise. Now, the big question, the question that determines how much rate we're using is basically, or how much time we're using is the length of this column, right? That's what determines the time I am using. Now, I don't need as much time as users. Why? I don't need as much time as users because the users are sparse. And I can resolve them if you want. I can resolve the value of this vector at the base station by requiring much lower number of time slots than the users. Okay? So you can already see that if I use a compressed sensing approach, I am reducing the feedback time. Instead of assigning a channel for each user, so basically n channels, how many channels do I need to assign here in this case? Yeah, which is what? S log n, right? S log n, where S is the expected number of active users, or expected number of users above a certain threshold. Okay? So now I can solve for this vector using compressed sensing. But there are more issues regarding to this problem. So this is how the algorithm is done. First, the base station determines the threshold, and it broadcasts it to the users, right? Then the users, they will check their SINR. Is it above the threshold? If it's above the threshold, they will be ready to feedback, right? Now, they feedback, okay? They feedback what? The value of the channel, or the SINR, times the code that they have, okay? The base station does compressed sensing, but the problem here is the following. This value here is basically the SINR. The SINR that the user should be serviced at, right? Now the problem here is that the SINR is noisy. So what do I need? If I serve the user at that SINR, there is a chance that this SINR is larger than the actual SINR, right? And if it's larger, what's going to happen? The rate will be 0, right? If I send him rate information at that rate, at that SINR, he's not going to be able to decode, so the rate will be 0. So what do I need to do? I need to back off. I need to reduce whatever estimate I do. I need to back it off, subtract some delta, so as not to lose the user. Okay? So basically what we do is this. Once we determine, so the base station determines the identity of the users, and in the second stage, it determines what? The value of the SINR. This is the SINR, so it will be many zeros and a few non-zeros, but these non-zeros will be what? Will be noisy. I need to back off. So what we do, we actually calculate the optimum value of the back off. Using random matrix theory, we can find what the value of delta that we need to use, okay, so as to optimally back off, okay? Because if we back off too much, we're going to lose the rate. And if we back off very little, we might be serving a user at a higher SNR than the actual SNR. Then there is an optimum back off that we can use. Okay? Mm-hmm.
It's not related to user I or it's the same. Again, it's something.
What do you mean? The delta?
The delta is the same for all the users.
Yeah, the delta, that's a good question. The delta is the same, I'll tell you why. Because what we do is this. If you want, we look at where's random matrix theory is used. Here's what it is. The MMSC error is this matrix here. This matrix here is the MMSC error, right? So what I want to do, I want to find the minimum eigenvalue of this matrix. Okay, that corresponds to the noise variance. Okay, so I'm assuming all the users to have the same variance. Okay, all the users to have the same, all the active users to have the same variance. So okay, and so now I look at this is kind of like a Wishart matrix. Okay, and I find I can find the distribution of the minimum eigenvalue. Okay, and from that I can determine the variance of the expected noise and corresponding back off. Is that clear?
If it's in statistic, it could be the same.
Yeah, yes. Okay, so, okay. So now there's another okay, so this is the feedback problem in a multi-user scenario. But there's one problem here. And I mean, up to, perhaps I'm wrong, but what we notice is the following. In the way people do feedback, they don't make use of the multiple antennas. Here, what we need to do this process for each beam. Remember, we have 3 antennas, so in random beamforming, we have 3 beams. So we need to ask which user is strongest for beam 1, which user is strongest for beam 2, and which user is strongest for beam 3. So how many time slots are we going to use? This way, we're going to use 3 times P time slots. Because what we're going to do this process here for each beam. Each user will either stay silent or feedback for each beam. I have P time slots, and I have 3 beams, so I'm going to have 3 times P time slots, right? Now, the question is, can I make use of the multiple antennas? Or in other words, can I feedback just once? And the answer is yes. So what happens in this case, what we do is the following. Each user is going to find the best beam for him, and he's going to send a 1, just a 1. What he's going to do, he's going to multiply, he's going to send a 1 divided by Hn times phi m. Hn is his channel, and phi m is the actual beam, okay? So he's going to do that. The base station is going to measure what it receives at each antenna. Each antenna is going to receive how many samples? It's going to receive P samples, right? And then the base station is going to do receive beamforming. So it's going to beamform along the same beams it's going to use for transmission. When it does that, what happens, I am going to get a vector, so I'm going to get a vector here, B times Vm, where Vm is either 1, if the beam is correct. Okay, so I'm going to beamform, so this is y times phi m. I'm going to beamform, so I'm going to get a vector with value 1 if the beam is the correct beam for the user, okay, or a value less than 1 or much less than 1 if it is not the correct beam. Okay, so what the advantage of doing this, what's the advantage of doing this, is that instead of feeding back 3 times P times, okay, I'm going to feed back just once. In other words, instead of just using 1 antenna at the base station for feedback, I'm going to use all the antennas at the same time so as to feedback. Okay, so let's end this with the simulation. So this is the performance versus the feedback SNR. This is the feedback SNR, right? How much noise is in the feedback, okay? And this is how we perform. So we are very close to we are looking at compressed sensing, structured sparsity recovery. We looked at the structure in A, structure in X, and structure in the noise. We are left with the structure in Y and a few others.
I didn't really understand how the user.
When you say that it's the rate, it's the rate.
Check جهانجير ايش؟
منين يا ولد؟
ايش جهانجير ايش؟
قول لي مثلا ايش فيك بقى ايش هذيك؟
ايش؟
لا قول ايش فيك؟
قلت لك ايش؟
قلت لك ايش فيك؟
ايش حاسي عندك كبر؟
لا لا ايش تقول ايش فيك؟ ابعد ثم معاك
فجاني هلال في
لا لا هو ضيع
ورحت جهانجير
لا لا لا
فجانجير خير
لا لا مش تبعك
Très bien.
Okay, welcome back. So what we've done so far is, if you want, just in a nutshell, we talked about how to solve an underdetermined system of equations. An underdetermined system of equation has many solutions, so you need to find a unique solution. So how to solve an underdetermined system of equation when the unknown is sparse. This is how you make the solution unique. You look for the sparsest solution, okay? And as we said, almost, you can argue with this, but almost any interesting phenomena has to be sparse. It's just that you need to find the proper domain where this phenomena is sparse, okay? So we said we're going to talk about solving an undetermined system of equations. Now, what we did, we added structure. So the structure could be structure in the noise, it's Gaussian. The second structure is structure in X, it could be block sparse. And someone would say, where is an application where it's block sparse? Actually, the feedback problem with multiple antennas, you can look at it as a block sparse problem. We can talk about it offline, okay? So that was the feedback problem. Okay, and then we talked about two applications. So we're saying structure in noise, structure in X, structure in A. What remains is structure in Y. We're gonna see it soon. But before that, we're gonna talk about a couple of applications. So the third application is PAPR reduction in OFDM. This is joint work with 4 of my students. 2 students are at KAUST, these master and PhD student, and 2 students at KFPM. Both of them are master students. Ibrahim is now at USC. Okay, so what is the PAPR problem? In OFDM, perhaps the biggest problem in OFDM is the fact that it has a high peak to average ratio. So this is a typical OFDM signal. This is the average value of the signal, and this is the peak value. And as you can see, the difference is huge. Now, why is this problematic? It's problematic because it overwhelms the power amplifier. The power amplifier has to work with signals with various strengths. Okay, and as maybe Luke was talking about yesterday, about power amplifiers of class A, class B, class C. Okay, so if you want to apply power amplifiers of class C, this will result in lots of distortion to the signal. So the signal has to be reduced, the PAPR has to be reduced before we actually are able to send it. Now, so basically, this is the power amplifier characteristic. This is the amplification versus the input. And as you can see, if the input becomes larger, then the amplification, here we'll have lots of distortion. So I have to back off the signal so that I will remain in the linear range. Now, there is lots of work that has lots of approaches for PAPR reduction. The problem with this approach, there are 2 problems with these approaches. The first problem is that they are of very high complexity. And imagine you have your mobile, and it's complex, right? You implement a complex circuit, so it will consume power. That's one thing. And the second thing, it will make it heavier. Okay, and the other problem is that basically what's called, most of them are based on what's called tone reservation. And in tone reservation, what you do is you reserve some carriers with no data, and you use them to reduce the peak to average ratio, but this is a problem because then you reduce the rate. Now we can look at this problem from a compressed sensing perspective. How is that? Well, the way we look at it is this. This is the OFDM signal. What we do is this. If we clip this signal here, like this, and get rid of the high peaks, then we get this signal here, and we send it. We send it to our receiver. Now, if we manage to, the clip part is sparse. This is the clip part here. So basically what we have is the transmitted part is equal to the original signal plus some clipping signal. If we manage to find C and subtract it, then we get back our original signal, okay? Now it's a sparse because the clipping signal is sparse. Okay, so this is the OFDM signal again. This is how it looks in the frequency domain. You can see these are QAM symbols. Now, what we're doing is we are reserving a few carriers which have no data. When we clip, this is the clipped signal, the whole data will be perturbed, including the free carriers. Now, as you can see, this is a typical compressed sensing problem, because what I would like to get is the sparse signal here that's clipped, and to get it, I don't need the whole Fourier transform, right? I can get part of the Fourier transform and still be able to get back my original signal. So if I observe the clipping only at the free carriers, then I should be able to get back my clipped signal, okay? Now, why can't I observe at the data part? Because it also contains the data. This one here contains the data plus the contribution of the clipping. Okay, so this is what we have. If we observe only on the free carriers, we have the following equation. Y is the Fourier transform, is the signal in the Fourier domain. C is the clipped signal, and I am observing only at the carriers which are free of the data. Okay, so that's why it only contains the effect of the sparse signal. It's sparse in the time domain. This is a partial FFT matrix plus noise, right? It's partial. Why is it a partial FFT matrix? Because I am only retaining the rows which have no data, only free carriers. Okay, so this is a typical L1 minimization, right? I have a long vector, basically an undetermined system of equations, so I can solve it using L1. Okay. Okay, now by now this is boring, right? We need something more interesting to talk about. So it turns out that there's additional structure that we can make use of. Remember, when I'm trying to solve for C, again, like any sparse recovery problem, I'm looking for two things or three things if you want. I'm looking for location of the non-zeros, and I'm looking for the value of the magnitude. The magnitude is composed of two things. It's composed of the magnitude and the phase, because usually the signal is complex. Okay, let's see if we can have some additional information about this. So first of all, I receive my signal. I equalize and receive the clipped signal. If I look at the clipped signal, this is the received clipped signal. From looking at the clipped signal, I can tell from the magnitude whether this is a candidate for a location, for a clipping location or not, right? If you look at this is close to the clipping location. What does it mean? It means that probably there was a clipping here that happened, okay? Why is it less? Because of the addition of the noise. What about these ones? There is a very good chance that these are clipping locations as well. They're above the clipping threshold because of noise. So from the received clipped signal, I could get a hint of where the clipping took place, or the support of the signal. That's one thing. So basically now, instead of doing this minimization, I can do this minimization here, where the weighting will help me find will tilt me towards the place where there's clipping, right? So I make W large at the places where there is no clipping, and I will make it small where there is clipping. Okay? So this is one piece of information that helps me find where the support is. Now also, it turns out that I can know the phase of the clipped signal. Why is that? Well, the signal that I receive, the origin signal is complex, right? So I can draw it this way. Each carrier has, each signal in time domain is a vector. When I clip, what I do is I subtract this so that it is within the clipping range. So the phase of the clipping signal is equal to the phase of the received signal. Okay? So that gives me an idea about what the phase is. So when I solve this problem now, I will already know the phase because that corresponds to the phase of the received clipped signal. And I can incorporate it here, so I no more need the whole of C, I need only the magnitude of C. Okay? So of C, of course, this is a complex system of equations. So what that means is that I can increase the number of equations, right? I can put them in real form and increase the number of equations. So that helps me get a better estimate of the magnitude of the value of the magnitude. Okay, so now I can incorporate the W to help me, that helps me figure out where the location is, and I can find the magnitude instead of just finding the complex original signal. Okay? Now, what's the problem with this approach? There are several problems with this approach. One problem is that I have to reserve some tone. I have to reduce my data rate because I am not sending in all data. So this is one problem. Is there a way where we can do without tone reservation? So what we could do is the following. We can do a data-aided approach. So remember, so for example, if you look at, so this is the data. I can, if I could guess that this is the value of this is here at the black line. The difference will be coming from where? Will be coming from clipping, right? And that's the data-aided approach. Now, in the data-aided approach, what's the problem with the data-aided approach for equalization or channel estimation? What's the problem? The main problem is error propagation, right? I could be using the wrong value of the data, and that would result in error propagation. Now, what we do is this. We rank the data according to how reliable they are. And we use only the reliable part of the data. Why is this possible? Why is this valid? It's valid because, remember one thing, in compressed sensing, I don't need many observations. I need a few observations, right? I need S log n. So if I only find a few data carriers which are reliable, then I can use them to recover the data vector. I don't need the whole data vector to be able to recover my clipping, okay? So for example, look at these 2 points, x1 and x2. These are the equalized received data. These are the 4 QAM constellations. Which one is more reliable? They're both equally close to this x. But one is more reliable than another. Which one? Yeah, they're the same, they have the same distance from x, but one is more reliable. x2 is more reliable, right? Because it's further from the remaining points. This one here, both of them are as close to x here, but this one is closer to x1, while x2 is further from all the points, if you understand me. So now we can have a reliability measure and calculate the reliability of all the data and only choose those data with top reliability, okay? And use them to recover the clipping, okay? So if we do this, then this is what we get, okay? So this is the bit error rate versus SNR. The lower curve is the case where I know exactly where the clipping happened, and I use least squares. This one here is where I clip, and I don't do anything after clipping. I just use the signal as is without correcting for clipping. This one, okay, let's see what one. this is the curve where I just find C, and this is the curve where I use the phase, and I account for I try to find the location of the clipping. Remember, I have two pieces of information that I can use, where the location happened and the phase of the data. So as you can see here, the a priori information helps me of the case where I don't use prior information. And it's very close to the Oracle least squares. Okay, now here's one more thing that we can do. We can use multiple antennas. Actually, in all these problems, it's very interesting. It will be natural to use multiple antennas. What's happening here is this. You have a CMO system. You're clipping your signal and you're sending your clipped signal. The clipped signal observed by all the antennas will be the same, right? So you have multiple observations of the same signal so that you enhance your ability for PA-PR reduction. Okay? So basically what we have for antenna 1, we have this, for antenna 2, we have this, etc. So we have more observations, okay? That will allow us to recover my clipped signal. What's interesting here is that it would kind of like counterintuitive to think that multiple antennas helps me with PA-PR reduction. If I did it, if we always did PA-PR reduction at the transmitter, definitely multiple antennas at the receivers will not help me. But now that I'm looking at PA-PR reduction at the receiver, then multiple antennas will help me. Of course, I can do all this complex processing at the receiver because I'm doing it where? At the base station. Okay, so here this is the results. So this is, okay, again, Oracle LS, assuming that I'm using two antennas. This is our approach without using the two antennas, and this is with using both antennas, and you can see we have a huge performance improvement. So this is one problem that we solved, okay? Clipping, we reserved carriers, but now, so we can do a data-aided approach. The second problem is this. What happens when you clip a signal? What's the problem with clipping a signal? It's gonna be a frequency distortion, right? I mean, you have multiple users, and you're gonna do distortion for all the users, right? You're gonna, overlap. If you're doing OFDMA, you're going to spill your clipping distortion to other users, right? So what do we do? How do we do? Well, it turns out, so for example, here we have users and subcarriers. The users should have been assigned independent carriers, okay? But as you can see, after clipping, each user occupies the whole band, okay? So how can we solve this problem? Well, it turns out now we can solve like we can solve we can recover all the clipping signals together. Okay, we have several sparse vectors that we recover together, and we can do it in an iterative manner. Okay, so again, this is we have two users, QAM 64, and then we have this is the Oracle. This is no clipping case, and this is the two user case. And as you can see, they are almost the same. Okay, yes. Right.
So in the 4G standard, like NDN also, we have the SCF-DMA. So you mentioned that we have the PR reduction by this approach.
Right.
Compared to SCF-DMA, what's the...
Well, I mean, I'm glad you mentioned this point. As far as I know, the reason why we use SCDMA is exactly to avoid this problem. Yes. So this shows the importance of peak to average. I can't compare two standards, but I'm just saying that it shows the severity of PAPR problem and how and the need to solve it. But I mean, in the downlink, you use right? Why? Exactly, or you can do PAPR reduction and afford the complexity. So what we're doing here, we're showing you how to relegate or transform all the complexity to the receiver, right? Yeah. Okay. Okay, so we come to the last structure, which is structure in the received signal Y. This is again work with Mudassir, who is a PhD student at KAUST. Okay, so here what we're having, this is the following, this is the multiple measurement problem. So what we have here, we have several systems of equations. Y1 equal to A1 X1 plus noise, Y2 equal to A2 X2 plus noise. There is nothing common between these equations except one thing. The x's have the same non-zero locations, the same support. Okay? So they are non-zero at the same locations, but the values at these locations might be different. Okay? So to show it to you in pictorially, what we have is this. We have, this is vector, this is y1, this is equal to some a times an x. This is y2 is equal to some a times another x. The x's have different values here, but the non-zeros happen in the same place, or in the same locations. So this is called the multiple measurement problem. So what needs to happen here, how can you can solve each one of these independently, right? But if you find the locations of this and if you give it to this system of equations, this will help you in the solution, right? So how can we do this? So this is the last structure, if you want. Now, where do we see this? We're going to see this in massive MIMO in a minute, okay, as an application. But here, like for example, you have an antenna transmitting, you have a CMOS system, and you have reflections. Okay, you have a CMOS system, so I'm a transmitter, and there are 4 receivers. The reflectors are going to be the same for all antennas, and so you expect the location of the reflection, right, to happen at the same place. So the impulse response seen by this antenna, this one, is going to be, it's going to have different fading values, but the location of the non-zeros will be, of the taps, of the active taps, will be the same. Okay, so what we did is, remember the SAB-MP, the algorithm which is agnostic to the distribution of X, we extended it to the multiple measurement case. And let's just see how things are done. Remember, in the SAB-MP, it's a greedy algorithm. Okay, so what the SAB-MP does, it finds the best first location and the best, then it adds to it the best second best and the third, etc. Now we can use multiple measurements in the greedy way. So what do we do? Let's look at it here. Basically what this does, this first antenna figures out, it says 13 is my first best location. Okay? For the second antenna, it says no, my best first location is the second location. And the same for this 30. Now what happens is that these 3 elements, this antenna 1 says, okay, maybe you're right, guys. So I'm gonna take all the guesses, and I'm gonna find the next, what would be the next one? Okay, and I'm gonna find the best one. So it turns out the best one for antenna 1 is this one here. Okay, and then I send it back. Similarly for this one, and similarly for this one. So what happens now, the central location will compare these 3, and we'll find, let me see. It will send these 3 to antenna 1 again. Okay, so initially the antennas are very different in what they see. This one sees 1312, this is 13.2, this is 13.30. But eventually, you can see that they converge. Notice, this one here did not think that 2 is a good choice, right? But eventually, it reached to it, right? Similarly here, for example, this one here did not believe that 30 is a good choice. But here, oh no, okay. This one here, first thought that 30 is a great choice, right? It began with thinking that 30 is a great choice, but eventually it dropped it, okay? So basically these guys collaboratively are able to figure out the location of the non-zeros. And the nice thing about this is that it requires only integer communication, right? Each guy is only sending the location of the tabs that think that they are the best tabs. Okay? Okay, so here, I mean, there are other algorithms suggested in literature that does this. Here, basically, we're plotting the success rate, how successful we are in recovering the location of the sparse vector versus the sparsity rate, versus how sparse the vector is. This is zero sparsity, meaning all zero, the vector has all zeros. This one here is 50%, meaning like 50% of the entries are non-zero. This is our success rate in the blue, and as you can see, we are much better than the other algorithms. Okay, so our success rate is very good. And again, this is a sub-MP, so we don't care about the distribution of the X. Okay, now here is one application where this could be used. This is single carrier FDMA, narrowband interference in a single carrier FDMA. So in LTI now we're using, in the uplink we're using single carrier. So here what we're having a wideband single carrier FDMA link, and then we have some interferers that are interfering. Okay, so this is the dual of the impulse noise problem. In the impulse noise, what did we have? We have a signal, and when we have impulses in the time domain. This is its dual. We have a signal in the frequency domain, and we have impulses in the frequency domain. Okay. Now, not only that, there's another problem with this actually. It turns out, you see, this is one system and this is another system. So when you actually sample, when you sample, the grids of the two systems might be not aligned. And so your impulse, what was an impulse in the frequency, spreads out because of the fact that things are not aligned. And so instead of having to estimate just a single pulse, now you have to estimate a spread pulse. Okay, so things become much more difficult. Okay, this is an example of a block sparse signal. Right? But why do I need to estimate a block sparse signal, like several values? Why do I have to do this when the original thing was actually very narrow? Okay, so this is because of the fact that the two transmitters are not synchronized, and they don't have to be. Okay, so what we do. What we actually do is we don't estimate the actual narrowband. We estimate a windowed version of the narrowband interference. It turns out that this is enough. And what we found is that if you use the Haar transform, then this would be enough. So we basically we don't estimate all of the interference. We estimate just a windowed version of the interference. Okay? So this is the performance. This is basically the no NBI case. This is the no NBI. This is with NBI, and this is the performance of our algorithm. So one would ask, for example, why are we doing even better when there is no NBI? Because what's happening is that even if there is noises with large amplitudes, like Gaussian noises with large amplitudes, we are able to get rid of it. Even if there is no NBI. I mean, the Gaussian noise itself might have large values that we are estimating and canceling using our approach, okay? Let's see. Okay, and then we can also do the data-aided approach, okay? So we don't, because now here we have to keep a few carriers to be able to sense the NBI. Okay, to sense the narrowband interference. Okay, now where is the multiple measurement happening? Where is it happening? Now imagine that the base station has multiple antennas. Okay, and it's receiving from this guy here, and it's receiving these interferers. Now the location of the interferers in the frequency domain, the interference in the frequency domain will be what? Will have the same location, right? But the values of the interference will be different. So now I have this multiple measurement problem. Okay, I'm trying to estimate these four guys. Okay, they have different values, but they have the same location. Okay, and then again, you see, this is This is with MBI, without removing the MBI. This is with I'm using multiple antennas, but I'm not making them collaborate, okay, in figuring out the locations, okay? I'm letting each antenna find it by itself. And this one here, when they actually collaborate with each other, two antennas. Okay? Any questions? Okay, so one more application, and basically this is distributed sparse channel estimation in massive MIMO. Okay, so Luke talked about massive MIMO, so he's the expert here. This is something that's like, very fancy, and we expect it to be like maybe in 5G. But one issue is channel estimation, and like Luke was talking about this, he gave a very nice overview of that. Okay, now, so what do you want? Now, one challenge in massive MIMO is the pilot contamination. So we need to reduce the number of pilots as much as possible, right? For each user. If I take any user, I want to reduce the number of pilots as much as possible, right? That's what I want to do. So how we can do that? Well, we can make advantage of the fact that the channel in the massive MIMO is sparse, okay? So if here we have, for example, this is the massive MIMO, okay, and this is one user, we have a CMO system, okay? So what we expect that the scatterers for the various antennas are what they are the same. And so we expect the channels for various antennas to have different fading maybe, but we expect the location of the tap to be the same. Now, we could say that, okay, the whole antenna grid has exactly the same tap locations, but this is a strong assumption. Or we could say that the tap locations are slowly varying. So if you can see here, in red, we have, so this is the central antenna, if you want. We picked one antenna, and this is its neighbors. This one has exactly the same locations. These ones are slightly varying, as you can see from the red tap. Okay? So now, this has, in the time invariant, so we have two cases, either spatially invariant, in which all the antennas have exactly the same support, or spatially variant. In the spatially invariant case, it becomes what? It becomes similar to the multiple measurement problem, right? Same, different y's, different x's, but the x's have the same support. But here, it's not exactly that multiple measurement problem. Okay, so what do we do now? What we're gonna do? So what's gonna happen is that each antenna is going to do the SAP-MP algorithm. Our algorithm which we developed, this support agnostic Bayesian algorithm. And it's a Bayesian algorithm. So what it can do, it can calculate the probability that a particular tap is active. Okay, so you have, like, for example, 32 taps. It says this probability is 0.001, etc. Right? This tap is 0.1, etc. It will give me the marginals of which tap is active. Okay? So it will give me. So each one of these is going to calculate a belief vector. Okay, of which taps are active. So this tap is active with probability 0, etc. Now what can happen? These beliefs are going to be shared. They're going to be sent to the central antenna. And what does the central antenna do? It's going to average them. And now this will be the new Bernoulli probabilities. Remember what we did in our algorithm? We said that each tap is active with probability P, right? And inactive with probability 1 minus P. Now, I'm running the same algorithm, but I'm saying, okay, I'm running it with different Bernoulli probabilities. The same Bayesian algorithm. Based on what? Based on what is measured and what information it got from the neighboring antennas. Okay, now this happens for each antenna. So, sorry. This happens for each antenna. So this one here is a central antenna, but also this is a central antenna when it communicates with its neighbors. So this will give its belief to this guy, this one will give it to this guy, and so on, right? Now when you iterate this algorithm, if you iterate it twice, 3 times, etc., So initially you have 0 neighbors, initially you have 0 neighbors, 4 neighbors, 12 neighbors, 24. You know, as you iterate more. So you collect more information, right? As you iterate more, right? Because each one is only taking from its neighbor. The next time it gets from its neighbor, the neighbors have gotten information from their own neighbors, and so things continue. Okay? Now, of course, you should not make D very big, right? Because why? What could happen? You start, things are spatially variant, and you start getting misleading information. So depending on how fast things are changing, or spatially are changing, you could make things fast, or meaning you can choose D. Okay? Okay, so this is how it's done. Each one runs the sub-MP. We calculate the belief, then we collect the belief from the neighbor, we average the beliefs, and then we run the sub-MP algorithm, and we re-estimate the channel, and so on. Okay? Now, here data aided could also be helpful, right? Remember, what do I want to do? I want to use the number of pilots. So I want to use data aided approach. But there's actually, I can do it in a more clever way. So as I said, so we're using OFDM. Each antenna will look at all the data and will choose the top, say, 15 reliable data, okay? As we said, for example, this X2 is more reliable than this X1, okay? Now here's what happens. These antennas, what happens is each antenna will calculate which carriers are reliable. And they will feed the indices of the reliable carriers to the central location. Okay? So they will calculate, for example, they will feed back the 15 top most reliable carriers to the now the thing is, these carriers might be different. The reliable carriers for this might be different from this, might be different from this, might be different from this, right? So what the central antenna does, it will take the intersection of these reliable carriers, and then what it will say, it will send it back to the antennas, and will tell them, not only to kind of improve the reliability even further, it will tell them, send me the data you have on these carriers. Because if these carriers are, so these carriers, first of all, I test the reliability, and then I test the value of the data on these carriers. The value on the data of these carriers should be what? Should be the same, because they're coming from the same user. So if the data is the same, it only retains, of this intersection, it will only retain those carriers which have also the same data. So this is what it's done. So they feed the reliability, each one feeds its reliability. This guy feeds back the intersection of the reliabilities, okay? And then these guys feed back the data on the reliable carriers. That would be my data that I'm gonna do use in a data-aided manner, okay? And this is, you can see the success rate. This is the success rate, meaning what is the percentage of reliable data I'm getting versus number of pilots. This is, okay, let's see. Sorry. This is the success rate of how many, of identifying the correct locations of the taps, okay? This is the success rate of identifying the correct location of the taps. So this is if I use only pilots. This is if I use pilots and data. And as you can see, the success rate is much higher. Why do I have two curves for each? This one, these two are pilots, and this is pilots and data. Why is this? I have two because in my algorithm, remember, what do the antennas share? They share beliefs, right? And these are real numbers. We have beliefs which are integers and beliefs which are real numbers to reduce the communication. I'm trying to reduce the communication between the antennas. So if I use only integers, then the performance will be worse than using the real numbers, okay? Okay, so yeah. So this is the performance. This is what I'm plotting here. I'm plotting the mean square error and the BER. This is for 4QAM, spatially invariant. And this is 4QAM spatially variant, okay? So the green line is the BER with the known channel, okay? And the red line is the BER with reliability and with yeah, with reliability, and this is with pilots only. And as you can see, we improve. This is the spatially invariant. This is the spatially variant for the Sup'Com, and again, the known channel and the channel with reliability, with reliable data and pilots does very well. Okay. Here we're comparing with the least squares. So assuming that the Oracle least squares. Remember, the problem is we don't know the location of the tabs. That's the problem. So the minute we know the locations, things become easy, right? It's the least squares problem. So this is the least squares, and this is our performance, okay? And as you can see, we do much better because we're using what? We're using reliable data. Okay? Any questions? Yes?
Is it a single user scenario?
This is a single user scenario. But again, here's what we're doing. We're saying this is a single user scenario. You are able, because of the sparsity, you are able to reduce what? The number of pilots. So, yeah. Yeah, I mean, you can do it in multi-user, but they're going to be on different frequencies anyway, and you can, right? Yeah. They're going to be on different frequencies.
Hopefully the channels will be orthogonal.
Okay, but even if they are not orthogonal, if you're using orthogonal pilot sequences.
Yeah.
Right? Yeah. Okay, so we talked about four structures, right? Which are basically structure in noise, structure in X, structure in A, and structure in Y, where we have multiple measurements. We can have one final structure, and I'm going to demonstrate it in this application. We can have the user-induced structure, okay? It's just like OFDM. OFDM, why is it very popular? Because of the cyclic prefix, right? It makes things just wonderful. Okay, so this is an application with my postdoc, Tareq, and Farouk, who was a PhD student at KAUST. Okay, so what's this application? What we want to do is we want to monitor the breathing of a patient. We want to do it with low complexity, and we want to also do it without putting so many equipment on the patient. Because the minute you put equipment on the patient, I mean, he's not going to sleep well, right? You're trying to kind of characterize his sleeping habits. Okay? So we want to do it in a wireless manner. So what do? We want, we're going to transmit ultra-wide pulses. These pulses are very narrow, so as to be localized very well. They're going to reflect off the chest of the patient. They're going to come back to you. Now, there are several problems with this issue. First of all, it's a very narrow pulse, okay? Meaning the frequency content is huge. And so if you want to recover the signal, you have to sample at a very high rate, right, by Nyquist's theorem. So this is one problem. The second problem is that the patient, he wants to sleep, right? He could be turning left, turning right, and the transmitter could be not in a direct line of sight. Yes? So because of that, you might not, the reflection will not be the direct reflection. First of all, there is a reflection from the room, not just from his chest, right? And also his chest might not have a direct line of sight with you. Okay, so this is the second problem. The third problem is that there might be movement in the room, right? I mean, you could have the fan on, or the curtain moves when you open the window, etc. Okay, so you want to solve all of these problems. Okay, yes.
You said that so the bandwidth is very large.
Yeah.
You are going to apply compressive size for that?
Yeah, but we're going to apply it.
There is no sparsity.
Okay, there is sparsity. Okay, we will talk about how to induce sparsity if you want. Okay, so what's done in ultra-wideband is people send several pulses, okay, and then they take the measurements from these pulses and they add them together. Okay, so first of all, so this is the pulse. Let's assume this is the pulse that we send, it's the first derivative of a Gaussian or second derivative. This is the pulse. So you're sending this and you get it back. Remember, this is very narrow, right? Maybe 1 nanosecond. So it means if you don't sample at a very high rate, what's going to happen? you're going to miss this pulse. For example, you might sample it here and then sample here. So essentially you lose it, or if you're lucky, you sample it here, or you sample it here. So for example, this is sampled at the proper rate, this is sampled at improper rate, okay? So if I reduce the sampling rate, if I simply reduce the sampling rate, I'm gonna miss many pulses, okay? This is one problem. Okay, now Dr. Awatif mentioned that things are not sparse. So how do we make...
If you apply compressive sampling in frequency domain, it's not sparse, but you are applying it in time domain.
Exactly, yes. Right, okay, so now, now you send these, so this is one problem, and we haven't solved it yet. Okay, now the second problem is this. The second problem is that reflections are not off the chest only of the sleeping person, but it's also off the walls, right, of everything that's in the room. Now what we do is this. What we do is the following. This is the tap value at one instant, and this is the tap value at the next instant. So if we subtract them from each other, right, the only thing that's moving is what? Is the chest of the patient, right? Everything else is not moving. So we expect, so this is how we sparsify the impulse response that we want. And these impulses are coming from where? They're coming from the movement of the chest. So this is how we create. So now what we want to estimate this sparse impulse response, okay? Okay, the third problem is this. The third problem is the following. If there is movement in the room, right? So what happens here, I'm plotting the impulse response that I'm observing with time. So you can see this is constant. Why is it constant? Because this corresponds to a wall. This corresponds to another wall. This movement here corresponds to what? To the chest of the patient. Now suddenly things change. One enters the room. So, right, he enters the room, but after he enters, or like, you know, a door closes or whatever, right? What's gonna happen? The room is back to its stationary behavior, okay? So what happens using our algorithm, so basically what we're gonna do, so at this instant, what we do is we subtract this instant from this instant, and we are able to get rid of the things that are common, and we are left with what? With the difference between this and this instant and this instant, creating what? A sparse impulse response, right? But of course, if we do the subtraction here with here, sorry, this one here with this one here, this will not give me a valid sparse signal. So what's going to happen? We will be able to recover the exact breathing pattern except for this, but we don't care. Why don't we care? Because we're going to, after we lose this tracking, we're going to track it. It's just like a small transient place where things are not gonna be able to, we're not gonna be able to get it. But otherwise, we're fine, okay? But we haven't solved one problem. There's one problem we haven't solved yet, which is what? Which is the subsampling, right? As I said, you're sending a pulse. You're sending pulses, and they are reflecting off the patient. If you have to sample at a high rate, or else you're not gonna be able to take the important part of the pulse, right? The pulse is what is very narrow. Okay, so I'm going to show you the solution of this in the next slides, but let me show you. So now we've solved it, and this is basically the estimation error versus SNR. This is our algorithm. This is our algorithm, and this is what's based on these squares. And matching pursuit. So as you can see, our performance is much better than the other algorithms versus SNR. Okay, now let me just explain how we solve the issue of this sampling. So what we do is this. This is what we do. What we want to do, these are the pulses that we're sending. Remember, we're sending a pulse of a width a nanosecond. Okay, and then we're remaining silent for say like 10 nanoseconds or 20 nanoseconds, and then we send another pulse. Okay, during that period, what's going to happen to the motion of the chest? So we have 1 nanosecond, 10 nanoseconds, and then 1 nanosecond for the second pulse. Well, actually there will be no movement, right? essentially no movement, right? Because the chest is moving at a very, very low speed, okay? So over these pulses here, over these pulses, the chest is essentially what? Stationary, right? So this is what we're gonna do. We're going to take the first sample from this pulse. If I subsample here, so I'm taking the first sample from this pulse, the second sample from this pulse, the third from this, the fourth from this, and the fifth from this. Now, if you can see, all of these are constructing a single complete pulse, okay? Now, what is the condition for this to happen? Is that the number of pulses and the sampling rate has to be co-prime. If they're co-prime, then you'll make sure that you're gonna actually construct the pulse. If they're not co-prime, then what's gonna happen? The first sample might be here, the second sample might be, for example, here, and the third might be. You will not be able to cover the whole pulse. Okay. So here, this is an instance of structure that is user-induced. We have induced that structure so as to be able to. Okay, and actually we do one more thing, which is, I mean, I'm in love with OFDM, as you have seen from the applications. What we do is basically, we add an auxiliary pulse here, okay? And that auxiliary pulse will make things circulant. So basically the sensing matrix we will end up with, previously if we don't put this auxiliary pulse, we will get this matrix. But with this auxiliary pulse, we get a circulant structure. And because of this circulant structure, like, you know, things become very easy. So when I solve, so basically I have to solve like a least squares problem. Okay, this is the original pulses, and this is the subsampled. So these are the pulses that I actually send, okay? And this is the subsampled pulse matrix. Remember, right? Because I'm not sampling all these instances, I'm only taking parts of them, right? I'm only taking parts of them, right? So this is the subsampling sensing matrix, and it's a circulant matrix. And now, because it's a circulant matrix, estimation becomes very easy, right? I mean, this is a circulant matrix. I can diagonalize it very easy using the FFT, and I get the estimation. I can easily get the estimation. All of these matrices are circulant. Okay, there's one thing that I don't talk about here, is that what if, you see, this means the only condition here is that these pulses has to be like really occur at the right instance. What if they are slightly, there's like, you know, a drift, a clock drift. So we deal with this problem, and then the problem becomes like, you know, estimation in the presence of uncertainty. And we can do like, you know, a robust least squares estimation. Okay? Okay. Yes, yes.
The aim of this application is forward.
Okay, the aim is this. The aim is to be able to track the movement of something that's slow as compared to RF speed. Okay? You know, any movement that's slow. Breathing, someone walking, etc.
For example, a sick person, for example, the breath of a sick person.
Exactly, yeah. So, right, okay. Yeah. So, you want to track movement in general, but the breathing is important because, like sleep apnea, there is sleep apnea, which is basically, sometimes the person will, his breathing will stop. Thank you for asking this question. Okay, I assumed in the back of my mind, people know. The sleep apnea, this breathing stops for a while, and then you want to observe that pattern, okay? And so that's why, and you want to do it in a wireless manner. You want to do it, we're going to put it at home, okay? So that's you don't have like, you know, you don't have to bring him to the hospital, right? And you want to do it with very low complexity, right? And you want to do it in a robust way. You're not going to constrain the patient, tell him like, you know, don't move when you're sleeping, whatever, right? Okay, and so we need to do this. So to make things, so we made things sparse by subtracting the measurements. We were able to sample at a very low rate, okay? So here I'm going to show you here the results. This is the mean square error versus SNR. This is all of these, believe it or not, all of these. This is at the Nyquist rate. This is sampled at 5 times below Nyquist, 10 times below Nyquist, 20 and 50 times. Okay? They are all exactly the same. Why? Because they are equivalent, right? All I have to do is I send more pulses, and I subsample at a higher, I subsample, and eventually I'm able to construct the actual pulse. So this is the error, and this is basically assuming that there is some drift in the clock. Okay, because the pulses are not exactly uniform, there is a drift. This is how we perform. Okay. Okay. So let me conclude here. So yes.
So the sampling period is not changed from location of the person.
No. What happens is this. Think about it. This is a person. Whether you send one pulse or you send 50 pulses, spaced enough, okay? He's not moving. I mean, the movement is like, he's very slow, right? I mean, the speed here is like, I don't know, like maybe like 2 kilometers per hour. It's very slow, okay? So if it's very slow, during that 50 pulses, nothing has changed, okay? So if you send one pulse, or 50 pulses and subsample them, you essentially get the same information, okay? So we're using that structure, okay? Okay, so this tutorial was about compressed sensing. It's about, in a very layman's term, it's about solving an underdetermined system of equations for a sparse vector. Okay. Now, as we've seen in all these, in the various applications, so one issue is the sparsity structure that we have used, but there are lots more pieces of structure that we have used, that we can use. One piece is, for example, the fact that the noise is Gaussian. One is that the matrix A is structured. One is that X is block structured, and one is the multiple measurement problem. Also, the problem itself might have its own structure that we saw, for example, in the PAPR reduction. We were able to tell something about the location of the sparse, of where the vector is sparse, or the support of the vector, or for example, its phase. Okay, so we've showed how to use all these pieces of structure, and we also showed that we could also, as a user, induced structure that helps you reduce the complexity. Thank you very much.
I have seen some work about combining compressed sensing with the candidate detector.
Thank you.
I don't know if you compared with they were looking for some specific pattern, okay, and they used compressed sensing, but not on raw data, on second order.
Right.
Yes, and they proved that it's more robust than working on raw data. I don't know if you have seen this work or. They call it candidate detector. They use a kind of template and they look for these templates, okay?
But this, they look for the second order. I mean, they use the second order.
Yeah, for example, you use the second order of the braid, signal or something like that.
Yeah, I mean, I'm aware of this work, where you, instead of dealing, as you mentioned, with the raw data, you deal with you take the correlation of the data.
Exactly.
And you use that. I mean, this is very clever. I've seen it. I know Louis Geert worked on this.
It's CPC. It's the daughter of Lagunas, in fact, Eva.
Okay.
She worked on this.
Okay.
And, Okay.
So,
anyway, I want to mention that
thanks.
could be interesting to look to the higher statistics.
Definitely, yes. Higher statistics, looking at higher statistics. This definitely is another structure to, I mean, just like you mentioned, this one very interesting thing is that the first people who used L1 for sparse recovery are the geophysicists. physicists. They like in the 60s, and this is how we kind of got. And actually, this this technique of looking at the second order statistics is also like done by geophysicists. It has a name actually. It's called. So what they do is you have sensors. You have sensors, and you look at the sensors. You kind of correlate. You don't look at the raw data of the sensors. You correlate the information, and this is called, I forgot, they have a name for this technique.
Yeah. She applied it also for the scene behind the wall. So you have the scatters that are fixed. Right. So if you detect this fixed pattern, you remove, so she can that they can detect if someone is moving, or in military application, right. Tracking is in radar right. Application. Right. Right. So they remove the wall, and they can see that right. The effect of the wall. Yes. And
yes.
Thank you.
Yeah, thanks. Yeah.
To reduce the PAPR, you suppose that the interference which comes from the other relays that are fixed to have a sparse vector.
From the other relays or from the other users?
No, there is a figure that we have the uplink and the user equipment, and the BTS is listening, and there is two interference.
Oh, this is, you mean NBI, narrowband interference?
Yes.
Yeah, okay.
Yes. So this interference, you suppose that we speak about that in the future there is not fixed relays. So, not fixed interference.
Okay. Yeah. Well, what happened here, by the way, we're assuming that in each single carrier FDMA symbol, the NBI could be moving. We don't require that it will be the same in all the.
Okay.
So if it's moving, that's fine. Yeah, we're doing we're randomly changing the NBI each packet. If it doesn't move, then your problem is much simpler. Right? Right. Yeah.
Thank you.
Okay. Okay. Thank you very much.
S'il vous plaît, juste pour info, n'oubliez pas, rendez-vous 8h30 à la réception pour le dîner gala. Merci. S'il vous plaît, aussi, n'oubliez pas d'apporter vos tickets, vos bons. Merci.